So let's go ahead and get into the bulk of this program. So there isn't actually too much in the way of a lot of methods we have to write for a hash table. We, remember, only have 3 public methods that we call. We have public put, which will put a key value pair, okay, key and v val, into the hash table. Let's cap that with a return null right now. Okay, let's also do the reverse of that. So you put something in and you get something out. So given a key, right, get a value out. Okay, and then finally, what are we going to do? We're going to do public boolean contains is there a key value pair with this key in it in the table. Okay. Let's see. Then we need 2 helper methods for this. The first one I'm going to put up here, private int find, which we'll write for put first, and then we'll adjust it as we need to. We'll basically co-opt it to write contains, and then get as well. Oh right, there's one more method after that. But let me just explain what find does. Find returns the index that we want to store key at, or that we can find key at, or the first null that we can find, the first null that we find, or rather empty space we find. I'll jump back to that, but basically this is the method that turns this key into the index on this particular hash table. Okay. There was one other one, which is put get and delete. So given a key value pairing, or sorry, given a key actually, we want to delete the key value pairing from there. Okay. So we're going to rewrite. So we're going to write it with regards to put, get, and contains first. So and then once we have to hit delete, we have to change. We'll have to make some minor changes to everything else. Once we figure out what the difficulties of delete is. Otherwise, and it makes more sense to do it that way, to basically go back and fix a few things, put one if statement here and there, rather than putting those if statements there to begin with and confusing the heck out of everybody. Okay, so we're going to work on find, put, get, contains, delete, and then we have one more private method. Let's go ahead and just actually move them down here for organization purposes. And private void rehash, we'll call it. And this is the method that will resize the array or the table when it gets too full. Okay, and we'll do that. We'll only resize when we add. So we're not gonna worry about shrinking our hash table as we remove stuff from it too much. Okay, and then one more method to write, but this one's not actually too bad. Public static void main. We'll write that for testing purposes. Okay. All right. So let's go over the find method first. So find, given a key, is going to find the index where I want to. Well, we're going to work on put first, and then we'll use the answers we get the answers we get from int to figure out how to do get and contains. So we'll just worry about given a key, how do I know where I want to put it? Right? Where does it need to go? Okay. And the answer is well, right? I mean, I mentioned this in class. What we want to do is just basically, well, it's a key. So first we have to turn it into an integer, right? Okay, remember that's problem 1. So problem 1, use hash code to turn that into an integer. Use a small array and grow it. And then we can mod by size to turn. Right, so first thing we want to do is that we're given an arbitrary key. It's probably not an integer because there's a lot of other things besides integers that we're going to use for keys. So we need to turn it into some kind of integer. And every object has a hash code, right? Public int hash code comes from java.lang.object. And so let's just review what this says over here. Returns a hash code value for the object. So it's supported for the benefit of hash tables, such as those provided by the hash map that they create. Okay? Okay, next, the general contract is whenever it's invoked on the same object more than once, then it's going to return the same integer. That makes sense. Basically, if you call hash code, it's always going to return the same identifier in the same program that's currently running. And we don't need to guarantee that if basically you stop the program and run it again, the hash codes are going to be the same between the two different runs of it, just in case you're running something like that. But we can use this. Let's see. Provided no information in using equal comparisons on the object is modified. So in other words, so long as basically, yeah. So if we change the object and it changes the equals, then we're allowed to change the hash code. Okay. If two objects are equal according to the equals method, then hash code must then calling hash code on those two objects must also be equal. So in other words, if I have object A and object B and A dot equals B, then A dot hash code should always equal B dot hash code. Okay. It is not required that two objects are unequal according to it. So in other words, what that one is saying, I'll write that last one out. If A dot, so if A, can't type today. If A equals B, if that is not true, if that's not true, that does not mean, it does not mean hash code. So two things are allowed to have the same hash code even if they're not the same object, right? That's kind of the big things there. But the idea here is that hash code, if you write an object, if you don't want to figure out how to write a hash code yourself, you can inherit one that does that. Otherwise, you can try writing your own hash function. Okay, so the first step was to, okay, we need so we're given a key, we want to find the index for it. Got a bit off track there, but I thought it was kind of necessary. So we've got a key, we need to find what index it's going to go to, and the way we do that is that we transform it into an integer, and then we put it, and then we modify the table size. Table length, int index, and that's good, right? That's all we needed, right? Well, unfortunately, no. If that was all we needed, I wouldn't have bothered writing a method about it. But the issue is that we have to deal is this third thing here. We don't have an infinite side array, so two keys may have the same index. So this operation, right, will result eventually with two things getting the same index, right? If I have a hash table of size 11, right, and there's 12 items that I've inserted, there's 12 keys I've inserted that are all different, then by the pigeonhole principle, which is just a really aptly named thing from statistics, we've got 12 keys and 11 slots to put them in, then one of those slots is going to have two keys going to it. So this gives us a good starting point, though, right? This will let us hit a location, okay? And once we hit the location, we can start, we can now address it. So the way we're going to resolve this is that if something's already there, we're going to use open addressing, okay? So first off, if index is equal to null, though, sorry, if there's nothing there in the table, though, table index is equal to null, that space is empty, in other words, okay, then I can just claim it, okay, like right, there's no collision going on there, the space is empty, I'm just going to claim it. Right now I'm going to return, okay, so right, that's one possibility number one. The space is empty, so I'm going to claim it. Possibility number two, it's not empty. okay, I have a collision, right? So this is actually pretty straightforward, even though I've been making a big deal about it. So take the key, turn it into an integer, modify the table length. Okay, that gives me a index that probably isn't necessarily unique, but if nobody's claimed that index yet, I'm going to claim it. That's where we're going to find it. Otherwise, if it's claimed already, well, while table index not equal to null. So while the table index is not equal to null, while there's something at that table index, what are we going to do? We are going to increment index. I've got to come back here. So we check the next index. Okay, so while table.index is not equal to null, well, I go on to the next one, and then I check it again. That's not equal to null? If that's taken 2, I increment, and so on and so forth. But unfortunately, this isn't as simple as just going index plus plus, because I could go to, index 45. So I'm going to use line numbers here: index 45, index 46, index 47, index 48, index 49, and say index 49 is the last index over in my array. So if I try checking index 50, I'm out of bounds. So we need to wrap around. So if index is equal to, so instead we do index is equal to index plus 1. Mod table.length. Okay, index is equal to index plus 1, mod table.length. That way we don't have to even worry about checking if we're going out of bounds. If we go out of bounds, go to index 49, the maximum index, and then go to index 50, well, 50 mod 50 will bring you to index 0, right? This will wrap around. If we need to, right, this is just like the circular array we did. So we do this while the index is not equal to null. Set the index, increment the index, and mod by the table length. And that's all we need to do. Okay? Except that's not quite true. There was one other kind of thing we need to do. Right? There's the possibility, right, that when we put something in the hash table, right, and I'm going to boot up my my Python interpreter because, again, speed here. So let's say we're going to go and say ht for hash table, right, and I put in the key value pair 3 hello. So the key is 3, the value is hello. And if I put in 3 again, but with world instead, it overwrites it. So there is one other thing that can happen, which is that I can, there's one other possibility besides it being null and not null. It could also, the index could also hold my value in there. Right? Okay, so this is turning out to be a bit more unorganized. So if table index equal to, so first off, if it's null, or if the table index, so if the entry there, the entry's key is equal to key dot equals the key that we're trying to insert, then we found the item, then we found the location our key is supposed to go into, right? If we find our key, that means we've already asked this question before and solved it, so we can use the previous answer. So means we just stop here. We found our own key, and we'll probably want to overwrite it if we're using put. Otherwise, while the table is not equal to null, and table index is dot key dot equals key. So while it's not null and it's not equal to ours. In other words, while we haven't found it, keep incrementing it. And then return index. If we do that, we don't need this anymore. So we can probably rewrite this to be a bit nicer, but I will do that in the next video since this one's getting sufficiently long.